Hello, once again, this is Bruce Wallenberg. This is Lecture 8B, the second part of our lecture on the unit commitment schedule. Remember once again that unit commitment is the process whereby we schedule generators on and off. We must have enough generators on to meet the load and spinning reserve, and if we don't have a sufficient amount of generation on, then we have to shed load. So we need enough generation on, but we don't want to turn too many generators on because that costs. The efficiency goes down and it costs more. Now, this lecture is going to start out with the topic of Lagrangian-relaxation. This is a method of solving unit commitment that overcomes many of the difficulties, for example, that we ran into in dynamic programming. Remember that it can explode. You have this dimensionality problem where you have all these paths from every state to the next state, and we had to curb that. We had to cut the paths off using just heuristic methods to reduce it, thereby giving ourselves giving up, I should say, on the absolute best solution, the optimal solution. So now we're going to start out here. We're going to invent this variable, and the variable has two states: a 1 or a 0. And it's 1 if unit I is on. Remember, this has got these subscript and a superscript. Subscript I means it's unit I, and T is the time period. So if UIT is 1, if the unit is on, if unit I is on during period T. So now I'm going to be multiplying this UIT times everything to tell you whether the unit is on or off. We're not going to draw a big diagram of states and time periods like we used to for dynamic programming. So the loading constraint, that's something that we have to meet, and it says the P load at time T minus the sum, and this is Pi of T is just the unit output of unit I during period T. And we multiply that times the UI of T. So if this is 0, well, then that unit doesn't have any output. It's off, so we don't even count it. But if it's 1, then that gets a 1 multiplied times the unit output. And it just simply says that the sum of the outputs must equal the load. So the P load minus this equals 0. Now note, this is summed. I equals 1 to n is the number of generating units. So it's summed over all generators. And we have our standard unit limits that say that this formula must hold up, or this set of inequalities. UI of T times the P min for that generator is less than Pi of T is less than the same multiplier again. Now, if this is 0, if this variable here is 0, well then, so it will be over here, and then this just says 0 is less than this is less than 0. It says this one's forced to 0. But it's necessary to have these upper and lower limit in there, and they apply in this case for every unit for every hour. So you've got summing up to 1 to n and 1 to t. Our objective function is got a sum over all the time steps and all of the units, and it simply says it's the operating cost here times the startup cost if the unit is online. Now see here, again, you have to go in and make sure that you multiply it by this, because if the unit isn't on, then there's no operating cost, and there was no startup cost if the unit in fact was off. So we say the variables then are f of Pi of T and Ui of T. That's the objective function. And then I'm going to put our standard Lagrangian, which says we have the objective function, which is this sum over all the time steps and all the units, plus lambda for our loading constraint up here, times P load minus UIT times PIT, as we did in standard economic dispatch. Only that there is one of these for every time step. Now notice that the lambda is got a T superscript. Lambda has a superscript, so there's T different lambdas, one for each hour. One for each hour. Now the idea of Lagrangian relaxation is as follows. The objective function, unit limits, and any min, up, down time constraints are separable. That's a key word here. They are separable over units, meaning what we do with one unit does not affect the cost of running another unit. Okay, does not affect the cost of running another unit. Now, it certainly will be affected through the loading constraint, and that's why I say the loading constraint is a coupling constraint, so that what is done with one unit affects all others if the loading constraint is to be met. And we've got this word relaxation up here, and what that means is that for one part of the overall solution process, we act as if one of the constraints isn't there, and then we solve. So we'll see what that is. So to solve, we ignore the loading constraint. It is said to be relaxed. This is done using what we call a dual optimization approach. We do one thing and then we do another step, and then we come back and forth. So we maximize the Lagrangian by adjusting lambdas, and then we minimize the same Lagrangian by adjusting the generator P and U values. And we do this over and over again. So there's an iterative approach. We just iterate again and again and again. We maximize the Lagrangian by adjusting lambdas. Then we fix the lambdas. Okay. Now we said we're gonna get rid of the loading constraint. Once these lambdas have been adjusted, we act as if they are fixed. And when we're minimizing the Lagrangian, we use fixed lambdas and we ignore the loading constraint. We're going to come back later and try to get that loading constraint in by adjusting the lambdas again, but we do these two different steps. So here's the dual optimization. This is actually comes up in the appendix of chapter 3. So here is the first step here, where we're maximizing the Q function over lambda, and then we find a value for each lambda t which moves Q towards a larger value. Assuming that it is found, in step 1 the lambdas are fixed, and then we do the minimization of the Lagrangian by adjusting the values of P and U. So let's work on this a little bit before I go any further. Here's our Lagrangian. Again, it's two sums, one over time and one over all the units. And this is the way we wrote it before. It's the F. This is the production cost of the generator times plus the startup cost. All of this times my remember, this is my 1 or 0 variable here, U, and here's all of the loading constraints over here. Well, I'm going to rewrite this. I'm going to start to rewrite this. I'm going to take this one here on the end. I'm going to break it up. I've got two things that I can break up. So I'm going to keep this part the same, and I'm going to break up and bring out lambda t times P load right here, and then I'm going to say minus the sum over the time steps and over the units of lambda t, pt, ut. Now, the second term, that's this term here, the second term, is a constant. As far as we're concerned, it's a constant. We can't do anything about it, and we're just going to drop it, since the lambda t's are going to be fixed as we close in on the problem. It doesn't play any part. And we write the Lagrangian then has these two sums over here. Okay, notice the two sums. They both appear in these terms. And I am going to switch them. I'm going to swap them around. So I'm going to put the t, the sum over the time steps, inside, and I'm going to bring the sum over the generators outside. So what this says now, if I have fixed the lambda, remember this is the step where I'm fixed the lambdas, that I've got an internal summation which goes over all the time steps, and it only applies to one generator I. There's I here, there's I there, I on this U variable, and I and I. And it does not, so what's inside these brackets here is only a sum, and it only depends on a particular, so I can break this up and I can say, well, look, if I'm going to minimize the Lagrangian, then I only have to minimize this for each generator, and I can do it without looking at what's going on the other generators. This is the relaxation. This is where I have separated things. So once again, this sum here gets pulled out, and it's down here. Same formula, but there's no sum over the I. I'm going to say I'm going to minimize this for each generator, and I don't care when I'm doing generator number 1. I don't care what happens to generator 2, 3, 4, and so forth. Then I'm going to do generator 2 and generator 3, and I just do them completely separately. So it can be solved separately for each generating unit. The minimum of the Lagrangian is found by solving for the minimum of each generating unit over the time periods. This is the minimum of Q of lambda. And so I'm doing this one at a time for each generator, and I'm doing it ignoring all the other generators as I'm doing a particular generator I. So I'm minimizing this function, subject to the up and down constraint, whether the unit is up or whether it is down, and whether it is at its max or min. So if the unit is operating, it must be between min and max. If it's not operating, it's 0. Everything in here is 0. And it turns out that we can do this by, what we need to do then is we need to determine the ui of t for every time step. Well, we only have one ui. Okay, once again, I'm only looking at the ui of t, and I have one ui for every time step. So here's my ui. I have these two states. Remember dynamic programming, where I have state diagrams? Well, here the state diagram has two states, a 1 and a 0. That's it. And the two states now have to be optimized. I have a state at time t equals 1, t equals 2, t equals 3, etc. So it goes over all of my time steps. If the unit is operating, then I have to minimize this function up here. If it is operating, if it goes from 0 up here, then I incur the startup cost. There's my startup cost. So, and then I do my dynamic programming the way we did before, where we would start out and we'd say, well, there's an F cost and an S and then a P, and then I also record the F cost, no S cost here, and a P for this state, and so forth. And then I need the optimum path across this. And I want to just come back to it here. What changes from one iteration to the next is the fact that these lambdas are going to change, and that will determine whether a unit goes on or off at any particular hour. So when ui equals 1, we have a startup cost. Since we're optimizing over p, if ui is already equal to 1, so then we're just minimizing this function here, f of p minus lambda pi. The minimum of this function is found by taking the derivative, and we just guess what? What does that look like? Well, it says that you force the unit to have an incremental cost df dp equal to whatever lambda we're setting. Well, if the lambda is such that the optimum value comes out less than the min, then you force it to the minimum. If it's within the min and max, when you do this, well, it comes out to, I call it p optimum, and if it comes out to be greater than p max, we force it to the max. So there's 3 different values for this min depending on where this came out. So if the lambda is a real high value, much too high, well, then the unit will not be able to solve, and we'll end up at the max. If it's way low, it'll end up at the min. If it comes out properly in between, then the unit will come out at a value in the middle. We're trying to minimize at each time step. We set u equal to 1, then this one will come out. We want that to be less than 0. Otherwise, we set it equal to u equals 0. So we want to do remember, we want to do a minimize. So we want this one to be less than 0. So, and remember, the value of this depends on the value of lambda, and depends on when we do that little economic dispatch on the unit itself. Now, we go all the way across. So this is done from t equals 1. I'm going to put some dots here just to indicate that we go all the way across to the maximum t. I just put cap t over here to the max. So I have to apply this, and this remember that there's a rule here that's telling us whether I should go to u equals 1 or to u equals 0. So what I end up with is I say, okay, here I turn the unit on, and then maybe I keep it on, then I turn it off, then I turn it right back on, then I turn it right back off, and then I keep it on for 2 periods. That's the kind of path. On, stay on, off, go back on, go down, and so forth. If there are minimum up and down times, you can apply them right within this up and down logic as well. Now, here is the second part of this. We have to adjust the lambdas. And so what we do is we come along and we say, all right, I'm going to try to just do a very simple gradient step. Lambda of t, I'm going to take the old value, and I'm going to take the derivative of my q function with respect to lambda, and I'm just going to use a little multiplier here called alpha. It's kind of a tuning constant. And what I'm going to do is I'm going to say if lambda equals, if this derivative is positive, meaning that the q is going to increase as lambda increases, then I'm going to let it go up. But once it turns around negative, this becomes negative, then I will reduce it, but I will dampen I won't let it go back down by the same multiplier. And this will help bring it into a solution. Now notice that I do this again for all the time. T equals 1 dot to t. So I got to do this for every t. I'm adjusting the lambdas. When I have adjusted the lambdas, I go back to the other steps. Well, here's a sample unit commitment solution. Here's 3 generators. There are their generator limits. Here's the load. It goes up from 170, 520 up to 1100 and back to 330, just for 4 hours. Now here is the table of, this is the way everything starts, and time goes down the page like this. Here's time, and we're looking at each hour. So the lambdas are all 0. Here's the u. These are the 1, 0 variables. Notice that there's one for every unit and one for every hour. Here's the P, the schedule, the output of the generators. Here is the load minus the PIT. Well, the load is, the UIs are all 0, so this has numbers in it equal to the load. Now, once we've gotten some schedules in here, this number should go to 0 for every hour. And this is what I call the PEDC. This is the value of the output of the generator when you dispatch it. And in order to make some sort of a measure of how well I'm doing in here, I'm gonna calculate this J star function, and I'm gonna say, well, and this is the, I'm gonna say J star minus Q star over Q star. Right now it's undefined because this is equal to 0. This should have an asterisk right here. So we start out and we say the next iteration, lambda t values have been increased. Remember, I took the dq dt and I increased them. Well, now I went, these are the values of lambda. I went 1.7, 5.2. Those numbers ought to look real similar. Remember, this is the Q function up here. And so these are the load values multiplied by that 0.1. So these are the numbers that I come out with here. And now f of p minus lambda p, I get these numbers here. This one happens to be negative. And the result is that when I do this, when I get to unit number 3, units 1, 2, they don't come on, but unit number 3 goes on during this period because this is negative. If this is negative, it'll turn it on, and then it comes back like this. It comes back down. So here's my optimum schedule. The optimum schedule for 1 and 2 is to just go right across the bottom and never turn anything on. So when I did that, I turned that on. Then I did iteration number 2. And when I did iteration number 2, I turned on the second unit. Then I did, you can see that I'm gradually turning these generators on. Then I did iteration number 3. Now look at the lambdas over here. And the lambdas are going to gradually converge to the solution. Here we've got the EDC values. Notice again, these EDC values are when, okay, I did the schedule and I put the generators online, and I did a very simple, on off, up and down. Then these were the values I got. And then I went over here and I did an economic dispatch, which changed that to the economic dispatch values over here. And this is what the J star number is the sum of all the actual operating costs. And I'm starting to get more units committed, and by iteration number 4, I have generators committed all the way through hours 2, 3, and 4, and finally this is iteration 5, and this and this is iteration number 6 down in here. And so I have finally got enough units committed. And this number, this is what's a key. This J minus Q star over Q is a measure of how close I am to the optimum. How close I am to the optimum. J is the operating expense. It's the sum of the actual operational cost when you did the economic dispatch, knowing which units are online. So here I had 1 online, here I had 2, here I have all 3, and here I have 2 again. And then I difference that with the value of Q. and I took the difference. So you take the difference and divide by Q, and you get a very, very small number. You'd like to drive that as small as possible, but that's the solution. And here are the lambdas. We adjusted the lambdas to get this solution. So that's the Lagrange relaxation solution. Now, if we come back to the same formulation, we can show how we set up an integer programming problem. Integer programming uses 1-0 variables. Remember that these are variables that come up inside the problem, and the program itself uses formulation very similar to Lagrange relaxation. There's a loading constraint with the UI variables. There's the minimum and maximum constraints. There's the objective function, same objective function, and then there's a Lagrange function. But the 1-0 programming or integer programming code will solve it directly. It doesn't use Lagrange relaxation. It uses its own techniques to solve. And as I said, this is becoming fast becoming the standard way of solving it now that these integer programming solutions have been developed. Here's an example of a week of load. Here's Sunday, so we're going out 24 hours here. Then we do Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, back to Sunday. And we notice that the load on Sunday is very low. Then Monday it jumps up. Tuesday and Wednesday are about the same. Thursday it grows a little. Friday we get a peak. And then Saturday the load goes back down low again, although it goes down just a little bit even lower on Sunday. And this is, again, typical of electric load on the power system. Each day the load goes between a peak and comes back down. The peak is during the day, and then it comes back down at night. So this represents 168 hours of load data. 168, 1 week of load. A very typical schedule for unit commitment. And we ran a program. This was a Lagrange relaxation program that my students and I developed. And you by the way, you can get this program off of our CUSP website, which through the web you can get this program and run your own example. So here's the load over here. This hour goes, I'd show it through 19, but it goes through 1 through 68. And here's the generation. I have 11 generators in this example. And you notice that the load is very low here, so it's only got 2 generators on. As the load gets up to around 1400, we put another generator on. These generators are all off. And we keep, so in this example here, up to hour 19, I never got beyond scheduling 3 units. Here's some other hours that are very high, 127 to 147. And once again, we got the first 2 on, then I got 4 and 5 on. Later on, I put on 6, and then I put them all on. So here I have a peak load, and I've got all the generators online. And then as the load goes back down again, it drops. It drops 4 units right here, and then starts dropping again 1 unit at a time until we get down to 2 units. Those are typical unit commitment schedules. Thank you very much.